This is a part 4 of module 2, spectroscopic techniques and application. Part 4 deals with nuclear magnetic resonance spectroscopy, and it has the following topics: principle, nuclear spin, precision of a nucleus, orientation of nuclei in a magnetic field, condition to be NMR active, relationship between radio frequency and field strength, chemical shift and factors affecting, shielding and deshielding, interpretation of NMR spectrum, how to draw low resolution NMR spectrum, spin-spin splitting, how to draw high resolution NMR spectrum, and MRI. What is the basic principle behind HNMR spectroscopy? All the atomic nuclei are electrically charged and also they possess a spin. When such a nuclei interact with an electromagnetic radiation, nucleus gets excited from its ground state to the higher energy level. Here the ground state is designated as the alpha state and the excited state as the beta state. The energy required for this transition falls in the radio frequency region of electromagnetic spectrum. Thus, we can say that when an atomic nuclei interacts with the radio frequency wave, nuclear excitation takes place along with spin flipping. So, before going to the details of HNMR spectroscopy, we should know what is a nuclear spin. The nucleus of an atom possesses neutrons as well as protons, where neutrons are neutrally charged species and protons are positively charged particles. That is, a nucleus has a net charge. All the subatomic particles like electrons, protons and neutrons can be imagined as spinning on their own axis. That is, they have a spin. So nucleus also has a spin. Any spinning charge body can generate a magnetic field. Likewise, a nucleus also produces a magnetic field. In the absence of an external magnetic field, the nucleus spin is randomly arranged. But when such a nucleus is placed in an external magnetic field, all the nucleus spins are ordered in a particular direction. The movement of nucleus in an applied magnetic field is known as the precessional motion. This nuclear precessional motion is compared to the movement of a spinning top. The precessional motion of a nucleus is associated with a frequency termed as Larmor frequency, which in turn depends on the strength of the magnetic field applied. In the absence of an external magnetic field, all these orientations of the nucleus are of equal energy. When a magnetic field is applied, the energy levels split into lower energy state and higher energy state, and each of this level is given a spin quantum number I. In lower energy state, the nucleus align in a direction of the applied magnetic field, and in higher energy state, they align in a direction opposite to the applied magnetic field. When the Larmor frequency becomes identical to the frequency of radio waves, resonance occurs and flipping of proton takes place with the absorption of a radio wave. The spin orientation of the nucleus becomes -half and will be in the higher energy level. The magnetic moment of the nucleus at this higher energy state will align in a direction opposite to that of the applied magnetic field. Not all the nuclei are NMR active. Only those nucleus which satisfy the condition, that is, spin quantum number I greater than 0 will be NMR active. For example, in the case of nuclei with even mass number and even atomic number like C12, O16, sulfur 32 are NMR inactive. The reason is, in such nucleus, the spins are paired against each other so that the net spin will be 0. In all other cases, that is, the nucleus with odd mass number with odd or even atomic number, and also even mass number with odd atomic number are NMR active. There is a mathematical relationship between radio frequency and the magnetic field strength. The energy difference between lower energy state and higher energy state of the nuclei is proportional to the applied magnetic field strength. When an electromagnetic radiation of frequency nu comes in resonance, delta E is equal to h nu, which is equal to gamma h b0 by 2 pi, and this is known as a Larmor equation. And so nu can be written as gamma b0 by 2 pi, where gamma is called gyromagnetic ratio and is a constant for each nucleus. This is a numerical related to magnetic field strength and radio frequency. The question is, if gyromagnetic ratio of carbon-13 nuclei is 1 by 4 of that of hydrogen-1 nuclei, what is the frequency to be irradiated to take carbon-13 NMR spectrum if the same instrument take HNMR spectrum at 300 megahertz? So the equation relating to the radio frequency and the magnetic field strength is nu is equal to gamma b0 by 2 pi, where gamma is called the gyromagnetic ratio, b0 is the magnetic field strength. Here we are having two nuclei, carbon-13 and hydrogen-1, and we take the NMR spectrum in the same instrument at 300 megahertz. So we can take the ratios nu1 by nu2 is equal to gamma 1 by gamma 2. So 300 by nu2 is equal to 1 by 1 by 4. And so nu2 is equal to 300 by 4, which is equal to 75 megahertz. Next topic, it's about the chemical shift. Different protons in a molecule gives signals at different frequency depending on its chemical environment. This shift in the position of signal due to a change in molecular environment is termed as chemical shift. The chemical shift is measured with respect to a standard chemical compound, tetramethylsilane, which is abbreviated as TMS, and is having a structure silicon with 4 CH3 groups. Why TMS is chosen as a standard reference compound to plot NMR spectrum? We have seen the structure of TMS with silicon and 4 CH3 groups. So it has 12 protons, all of them are identical, and it gives only one signal. Here the silicon is having a plus I effect, and so the protons are highly shielded, and hence the delta value is almost 0. The compound is chemically inert and is soluble in most of the organic solvents. The mathematical expression of chemical shift delta is equal to nu sample minus nu reference divided by operating frequency expressed in megahertz. So this is a numerical related to chemical shift. The question is, when HNMR is taken using 100 megahertz instrument, the signal for the proton in chloroform appears at 728 hertz, higher from the TMS signal. Calculate chemical shift. Here, nu sample minus nu reference is given as 728 hertz. So delta is equal to 728 divided by operating frequency, which is 100, which is equal to 7.28 ppm. What do you mean by shielding and de-shielding of a proton? When a molecule is placed in a magnetic field, its electrons are caused to circulate and produce a secondary magnetic field. This secondary magnetic field is known as induced magnetic field. This induced magnetic field may oppose or reinforce the applied magnetic field. Thus, the two possibilities are: if the induced magnetic field opposes the applied field, the net field felt by the nucleus will be less, and hence the nucleus is said to be shielded. And if the induced magnetic field reinforces the applied field, the net field experienced by the nucleus will be high, and the nucleus is said to be deshielded. There are different factors affecting chemical shift values. The first one is electronegativity. As the electron density around the proton decreases, shielding effect decreases and delta value increases. Consider a CH3 proton in different environments of fluorine, chlorine, bromine and iodine. As we move from fluorine to iodine, the electronegativity decreases and hence the delta value also decreases. So, of all the four compounds, the CH3 proton in fluorine environment experience maximum deshielding effect and hence shows the high delta value 4.3. Second one is cumulative effect of electronegative substituents, that is the number of electronegative substituents. As the number of electronegative atoms in a compound increases, the deshielding effect increases and so the delta value increases. In the first compound, we can see there are 3 chlorine atoms. In the second one, there are 2 chlorine atoms. And the last one, we are having only 1 chlorine atom. So the first compound with maximum electronegative substituent shows a high deshielding effect and hence a high delta value 7.3. Another factor affecting the chemical shift value is distance from the electronegative atom. When an electronegative atom is substituted in the hydrocarbon chain, the electron density around the proton decreases. So, the proton closer to the electronegative atom experiences maximum deshielding effect and hence shows a high delta value. As the distance from the electronegative atom increases, the deshielding effect decreases and hence the delta value decreases. Deshielding and shielding are another factors affecting the chemical shift. In deshielding, the induced magnetic field reinforces the applied magnetic field and hence the delta value increases. And in shielding, the induced magnetic field weakens the applied magnetic field and hence decreases the delta value. How to interpret a chemical shift in a molecule? From the NMR spectrum, we can deduce 3 factors. The first one is number of kinds of proton. This can be obtained from the number of signals we obtain in the NMR spectrum. Second one, the nature of chemical environment. And this nature, it is directly related to the position of signal. And the third one is number of protons present in each chemical environment. And this is related to the intensity of NMR signal. Below is the NMR spectrum of ethanol CH3CH2OH. In the spectrum, we can see 3 signals, which shows that ethanol has 3 different kinds of proton. Also, the 3 signals are formed at 3 different delta positions. That is, the proton which is directly attached to the electronegative atom oxygen will forms a signal at high delta side, and as the distance from the oxygen increases, the delta value decreases. And the last one is, we can see the 3 signals are of different intensity. The one with maximum number of proton, that is CH3 groups, has the maximum intensity, and the one with minimum number of proton, that is OH, has the minimum intensity. How to draw a low resolution HNMR spectrum? To draw the spectrum, we have to follow 4 steps. The step 1 is, first you mark the different types of protons present in the given chemical compound. For example, in CH3OH, we are having 2 types of proton. One is CH3 proton, another is OH proton. So you mark it as A and B. Here we are having 2 types of proton. Second one, CH3, CH2, CHO. Here we are having 3 types of proton. One for CH3, another for CH2, and third one for CHO. And the last one, CH3O, CH2Cl. Here we are having 2 types of proton. One for CH3, another for CH2. Second step is, if a compound is having similar groups, we have to check its chemical environment. For example, CH3, CH2, CH3. Here we are having 2 similar groups CH3. But both CH3 groups are having the same chemical environment. So they should be treated as one. So in this compound, we are having only 2 types of protons, A and B. In the compound CH3, CH2O, CH3, again we can see 2 similar CH3 groups. But in the first CH3 group, its chemical environment is CH2 group. And in the last CH3 group, its chemical environment is oxygen. That means the 2 CH3 groups should be considered as different. Hence, here we are having 3 types of protons, A, B and C. Step 3 is, arrange different types of protons according to their delta value. That is, the proton directly attached to the electronegative group will have a high delta value, and as the distance from the electronegative group increases, the delta value decreases. For example, in compound CH3CH2Cl, here we are having 2 types of protons, A and B. The B proton is directly attached to the electronegative atom chlorine. So B is having high delta value than A proton. Second compound, CH3CH2CH3. Here there is no electronegative group present. In such situation, the group with less number of protons will have a high delta value. So here the CH2 proton is having high delta value than CH3 proton. If a compound is having more than one type of electronegative atom, then the proton attached to highly electronegative atom will have a high delta value. For example, in the compound fluorine CH2CH2Cl, here the A proton is attached to fluorine, so A proton is having a high delta value than B proton. And finally, in step 4, we draw the NMR spectrum with delta value in the x-axis and energy in the y-axis. The reference compound TMS is shown at delta value 0, and the height of the peak depends upon the number of protons in each chemical environment. So these are a few examples to draw the low resolution HNMR spectrum. The first compound is methanol CH3OH. So in step 1, we identify the number of types of proton. Here there are 2 types of proton, A and B. And in step 2, we check for any similar groups are present. Here there are no similar groups present. And step 3, we arrange according to the delta value. Here the B proton is directly attached to oxygen. So B proton is having high delta value than A proton. And in the fourth step, we draw the NMR spectrum. TMS, it is shown at the delta value 0. At high delta side, we draw the signal for B proton, and at low delta side, we draw the signal for A proton. And here, A proton is having more number of protons and its height is higher than B proton. Another example is CH3, CH2, CH3. This compound, it is having two similar CH3 groups with similar chemical environment. So, the two CH3 groups should be treated as one. Thus, this compound is having only two types of protons, A and B. And to arrange these protons according to their delta value, here we consider the number of protons. The B proton is having lesser number of protons, so its delta value is higher than CH3 proton. Next topic is spin-spin splitting or coupling. Every hydrogen nuclei in a molecule spins and generates their own magnetic field. Magnetic moments of these magnetic field can interact with the magnetic moment of external field. This causes a splitting in the NMR signal. Thus, spin-spin splitting can be defined as a splitting of NMR signals due to the coupling interactions with the neighboring proton. How will you determine multiplicity in spin-spin splitting phenomenon? We have seen that in low resolution NMR spectrum, single peaks are observed, but under high resolution, these signals can split into several signals, which is known as multiplicity. Thus, multiplicity of a particular group depends on the number of protons at the adjacent atoms and follows n+1 rule, where n is the number of protons on the adjacent atoms. If the proton on atom B is affected by the protons on atom A and C, which are not equivalent, then the multiplicity observed for B proton is calculated using the equation Na+1 into Nc+1, where Na and Nc are the number of equivalent protons on A and C. And if the protons on atom B is affected by the protons on atom A and A star, which are equivalent, then the multiplicity observed for B proton is calculated using the equation Na plus Na star plus 1, where Na and Na star are the number of equivalent protons on A and A star. So we have seen three different rules to follow to determine the multiplicity. The separation which we see in a multiplet is known by the name spin-spin coupling constant J. The value of this J decreases with the distance between the coupling group, and the intensity ratio at which the multiplet is observed is determined from Pascal's triangle. So this is a Pascal's triangle to determine relative intensities of multiplet observed in the NMR spectrum. If the multiplicity is 1, we observe a singlet peak in the NMR spectrum, and if the multiplicity is 2, the relative intensities of multiplet will be 1:1, and it is known as a doublet. If the multiplicity is 3, the intensities of the multiplet will be 1:2:1, and it is known as triplet. If the multiplicity is 4, the relative intensities will be in the ratio 1:3:3:1, and it is known as quartet, and so on. So these are some of the examples to draw the high resolution HNMR spectrum. The first example is ethyl bromide. The chemical formula is CH3CH2Br. So the first step is to identify and mark the number of equivalent protons. Here we can see that there are CH3 protons and CH2 protons. So we mark it as A and B. So the number of NMR signals observed is 2. The second step is to apply n+1 rule. The nearest neighbor of proton A is B, so we apply n+1, where n is the number of protons in B. So 2 plus 1, it gives 3. The nearest neighbor of proton B is A. We apply n+1 rule, where n is the number of protons in A. So 3 plus 1, it gives 4. The third step is to determine the peak intensity from Pascal's triangle. For multiplicity 3, the relative peak intensities will be in the ratio 1:2:1, and for multiplicity 4, it will be in the ratio 1:3:3:1. So this is a high resolution spectrum of ethyl bromide, where CH2 forms a quartet and CH3 forms a triplet, and here the CH2 proton is directly attached to the electronegative bromine atom. So this proton is highly de-shielded and appears at high delta side compared to that of CH3 proton. One of the main application of NMR spectroscopy in medical field is magnetic resonance imaging, MRI. Medical imaging technique is used in radiology to visualize internal structures of the body in detail. MRI makes use of the property of nuclear magnetic resonance to image nuclei of atoms inside the body. Human body tissues contains lots of water and hence protons, that is hydrogen nuclei. When a person is kept inside a strong magnetic field and when radio waves are applied, these hydrogen nuclei will absorb the radio waves and get excited to higher energy level with spin flipping. Once the radio frequency current is turned off, these nuclei will return to the ground state and will align parallelly. This process is known as relaxation. During relaxation, the nuclei will lose energy and emit their own RF signal. This RF signal is measured by using a receiver coil and is then processed and reconstructed to obtain 3D images. Depending on the type of tissue being scanned, this relaxation time varies. The computer will record the time taken by the molecule to realign themselves, and this helps to detect different types of tissues. Thank you.